I welcome all of you to the class, and today we'll be talking about the second solution of the gyroscopic motion, and today we'll talk about the torque-free motion. As far as the torque-free motion is concerned, to the equations of motion of gyroscope, which are simply the applications of the Euler equations of motion, the torque-free motion is described as one of the solution of the gyroscopic equations of motion. So if we recall whatever we have done till now in this kinematics of rigid bodies in 3 dimensions, it all started with the equations of motion in 3 dimensions, which we described as the Euler equations of motion. And then we started applying the Euler equations of motion to some physical objects, and the topics or the physical objects over which we applied the gyroscopic equation, over which we applied the Euler equations of motion, was the gyroscope as a rigid body. Then, understanding the equations of motion of the gyroscope, we finally try to solve the equations, and we stated that it has two solutions. One is the precision, steady precision, and second is the torque-free motion. Today we'll talk about the torque-free motion. As far as the torque-free motion is concerned, it is the motion of a body which is essentially caused by gravity. Okay, the only external force acts on the rigid body is the force of gravity. Then, when the motion of a body is described in such a way that the body itself is acted upon by no other external force except the gravity, then the motion of the body is called the torque-free motion. So, if you look at the torque-free motion, we have been describing it as the motion when the only external force acting on the body is the gravity. Okay, then the general motion of the body is called the torque-free motion. So as far as the torque-free motion is concerned, the torque-free motion is the motion of a body under the influence of the gravitational force. Only the external force acting on the body is the force of gravity. I will give you an example. In your lower classes, you have talked about the projectile motion. Okay, so what we had, we usually take a projectile, and this projectile is fired at some angle. Okay, so we have some projectile in hand, and the projectile is fired and it follows a parabolic trajectory. Okay, so at any position of its trajectory, like this position, okay, this projectile is under the influence of the gravitational force. Okay, if we so this motion of the projectile, we can also call this as a torque-free motion. The motion of the projectile is also classified, can also be studied as a torque-free motion, because during the entire course of motion of the projectile, the only force acting on the projectile is the force of gravity. When we neglect the effect of the air resistance, okay, because as the projectile is as the projectile is following its trajectory, there will be definitely air flowing over it. Okay, and that air flow over this projectile will offer some resistance. Okay, so we know what we call as a drag force. Okay, so drag force is one of the force, or drag, what we call as. So drag is the force apart from the gravitation which will be acting on this projectile. But if we assume that the drag is zero, there is nothing like that of drag. Okay, so the only force acting on the projectile is the gravitational force. Okay, so we can classify this motion of the projectile, while we neglect the drag, as the torque-free motion. In the same way, we talk about the motion of the satellites. We are having the satellite launch, and when the satellite, so we are having the what we call as the boosters. Okay, so or something, or some engines. Okay, boosters give thrust. So we essentially have the rockets. Okay, like this. So in the front portion of these rockets, we are having the satellites. So we have a satellite over here, and this satellite is to be launched in space. Okay, the satellite is to be launched somewhere in space. So what we have in this rocket, we are having the boosters. Okay, the function of the boosters is to give thrust to this rocket, to launch this rocket into the space. Okay, so you have the what you call as the boosters attached with this rocket. Okay, so some fuel is burned. Okay, so as the fuel burns, it gives thrust, and essentially this rocket goes into the space. But as this rocket goes into the space, essentially a stage reaches where these boosters are detached. Okay, in its overall flight, the boosters are detached. Okay, so as the boosters get detached, then the overall motion of the rocket, of the satellite, is simply under the influence of its gravity. There is no force acting on it. The force that was initially created, that is the thrust, that was created by these boosters. Okay, but a stage reaches where these boosters are detached, so there is no thrust created by the boosters, and the only force that acts on the satellite is the force of gravity. So we can classify the motion of these satellites in space as the torque-free motion. And once we study the torque-free motion, let's assume the body to be the axisymmetric body. The body is symmetric about some axis. That is what I mean to say. Let's study this torque-free motion over this body as is given in your textbook. Okay, this is a satellite image. This is an image of a satellite. Okay, in space. This image of the satellite in space. This is the image of a satellite in space, and this satellite in space that we are talking here. Um, is under the influence of its gravity, because initially this satellite would have been a part of some of a rocket. Okay, and rocket is provided with the thrust by the boosters. The boosters at some stage of its flight get detached, so finally what goes into the space is not the rocket, is simply the satellite. So let's talk about this satellite. Okay, and we say this satellite is axisymmetric. Okay, if you take a cross section over here, if you take a cross section at point G, you will simply get this cross section to be a circular cross section. Okay, so this cross section, if you take over here, this cross section is a circular cross section. Okay, and if you draw an axis like this z axis over here, okay, if you complete this z axis as is drawn here, which I will just explain you, this axis z divides this satellite into two simple symmetrical portions. Okay, two symmetrical. This portion I will call this as portion 1, and let me call this as portion 2. The portion 1 and the portion 2 are symmetric portions about z axis. That's why we call this as this is axisymmetric. Okay, though we can study the torque free motion on non-axisymmetric bodies, but axisymmetric makes the analysis simple, as we will just see. That's why we are talking about the axisymmetric objects. Okay, so let's talk about these axisymmetric objects, torque free motion. Okay, let's suppose we simply have this satellite. We don't have this x y z axis right now. Okay, we do not have these axes right now. We are free of all these axes. We simply have the body. Okay, we simply have the satellite. Now, we said that there is no external force acting on the satellite. We know summation of all the moments about the center of gravity, okay, is equal rate of change of the derivative of angular momentum about the center of gravity. We have already done this. In fact, we have derived this as well. That is the summation of all the moments about any point of a rigid body is equal to the derivative of the angular moment about that point. So we are talking about the point G, which we assume to be the center of gravity. Then the summation of all the forces, a summation of all the moments about an axis passing through point G has to be equal to the angular momentum, derivative of the angular momentum of the rigid body about an axis passing through G. Since we know, as far as this moment is concerned, it's equal to the external force F cross R, okay, force into force arm. Since the external forces on the rigid body are zero, therefore this moment too has to be equal to zero. Okay, we don't have any external force acting on the rigid body. When you don't have any external force acting on the rigid body, then the F is equal to zero. Therefore, the moments are also equal to zero. Fine. When the moment is equal to zero, and you have a derivative of the angular momentum to be equal to zero, we know when the derivative of an physical quantity is equal to zero, then that quantity is an isolated constant. Okay, because for all the constants, for all the isolated constants, the angular momentum is for all the isolated constants. Okay, the derivative is equal to zero. Okay, so the question is, if you have this equal to zero, if you have hg dot equal to zero, that simply means that hg is constant. Okay, so if you write it, I will write it just as, let me just pinch it first. It's like then hg happens to be constant. I will write this as hg is equal an isolated constant. Okay, since hg is vector, okay, it means its direction as well as its magnitude both are fixed. Okay, and we select, in order to do the analysis, what we do, we select an axis. Okay, we select an axis, that is this z-axis. This is point G about which we are taking all these moments. This is the center of gravity of the satellite, and we select this axis, okay, to be the capital Z axis, about which we assume that this angular momentum of the rigid body is acting. Okay, so we assume that the angular momentum of the rigid body at G, which is constant in magnitude and direction, is always acting about this capital Z axis, okay, which we are assuming to be this axis. Fine, no issues with this. This is an assumption. Okay, we assume that hg is along this capital Z axis. Fine. Now with respect to this axis coordinate system, with respect to this point G, we select one more axis, that is small z axis, and we select one more axis, that is small x axis, and we select one more axis, that is small y axis. As far as this small x, small y, and small z axes are concerned, these form small x, small y, and small z. It forms our rotating frame of reference. It forms our rotating frame of reference. Okay, this is our rotating frame of reference. Small x, small y, and small z, which are perpendicular at a point G. They are perpendicular to each other at point G. Fine. Now we are assuming the angular momentum to be about capital Z. Capital Z we are assuming to be along a direction. Okay, this is a direction which till now we have been denoting as a z-axis or the ground frame of reference. Okay, so if I can complete this, I can simply write it as I can write this as an axis which is perpendicular to it. I will draw it like this. Okay, I will draw it like this. That is my one more axis, and another axis I will draw like this. Okay, so I will call this as, this is my capital X and this is capital Y. This capital X, capital Y, and capital Z, this is also perpendicular to each other at point G. It represents my, this represents my ground frame of reference. Okay, it represents my ground frame of reference. Fine. So we have a point G. At point G, we have first obtained that hg is constant, that is angular momentum is constant. It is a vector quantity. It will be constant in magnitude and direction. By being constant in magnitude and direction, we are assuming it to be along capital Z axis. And we are saying that capital Z is a Z axis of the ground frame of reference, having capital X and capital Y as another two axes. Apart from the ground frame of reference, we are having the small x, small y, and small z as the rotating frame of reference. Okay, let me rub this all. Now I will just do the analysis. So hg is constant as is written here. Hg is constant. Okay. Now this hg, which we are assuming to be about capital Z axis, we are assuming that this Z axis, ground frame of reference Z axis, and the rotating frame of Z axis are at an angle theta with respect to each other. Therefore, we can resolve this hg into two components. One component will be along Z axis, along Z axis, and its another component will be along y-axis like this. Okay, so we can write this as, this is hg, this is hg cos theta, and it's along z-axis, it's along k cap, that's written here, hg cos theta along k cap. And it's having one more component, that will be hg, that is hg sine of theta, and it will be along y-axis, that is hg sine theta y cap, that is here. Hg sine theta y cap is over here. Okay, so this hg, which we are assuming to be about capital Z axis, and number two assumption is we're assuming that capital Z axis is subtending an angle theta with respect to small z axis. Okay, therefore this hg can be resolved into small y and small z axis as hg sine theta j cap and hg cos theta k cap. Fine. Now we already know the equation. The equation that we already know is the equation of hg. We have already derived this equation. That is, angular momentum of a rigid body in 3 dimension is given as, hg is given as moment of inertia about x-axis multiplied by component of angular velocity along x-axis. Moment of inertia along y-axis multiplied by component of angular velocity along y-axis. Component of angular moment of inertia about z-axis multiplied by angular velocity component along z-axis. This is small x here, this is ix, and this is iy over here. There's a little correction. Okay. Now, this is already derived. If we compare, this is the general equation of the angular momentum. If we compare hg, the general equation of hg, with this equation of hg which we have obtained, then we can easily, as we balance it, then we are having I omega x I cap. We do not have any omega I cap here. So we'll write this as, this is O vector along x-axis. Okay, if we compare both the two, we'll first of all obtain the angular velocity omega x has to be equal to 0. Okay, you have a component here, you don't have a component. Both these are the same vector equations. Okay, so omega x is 0. That's one thing. The second thing that we can obtain is about the omega y. I omega y, that is I omega y here. I omega y, I omega y is along the j axis, j cap, that's equal hg sine theta. Okay, that's equal hg sine theta. And the third component we'll obtain is iz, by the way, this is iy. Okay, and the third component is iz omega z. The z components, once we start to balance, it will be equal to hg cos theta. So it's here hg cos of theta, that's okay. So we can obtain the components from here. So from these equation, omega x is equal to 0. There is no component of angular velocity along x-axis. There is no component of angular velocity along x-axis. As far as omega y is concerned, that is hg sine theta divided by iy. As far as omega z is concerned, that is hg cos theta divided by iz. That is the equations that we obtain are given over here. These equations: omega x is equal to 0, omega y is equal to hg sine theta divided by, this is iy. Okay, and omega z is hg cos theta divided by iz. Okay, now the total omega is, as just we have written, omega is equal I x omega x I cap plus iy omega y along j cap plus iz omega z along k cap. Okay, this is what we have already written, iz omega z along k cap. Okay, now omega x is equal to 0, therefore this entire component is 0. Okay, omega will come out equal to iy omega y. Okay, that's equal, omega y is hg sine theta divided, oh sorry, not I, sorry, this is not I over here. Okay, this is I is when you have angular momentum on the left hand side, sorry. So you have omega x omega y and omega z, that's equal, this term is equal to 0. Omega y is hg sine theta iy j cap, that's here. In place of omega y, we'll write this expression. Okay, that's what we have written here. And in place of omega z, we'll write this expression. Okay, so this expression is written over here. Okay, so the total angular for torque free motion, you just try to understand this torque free motion. The body is having angular, this is something new for us, because we know if a body is rotating, if a body is rotating about some axis, if a body is rotating about some axis, then some torque must be acting on it, and torque is related to angular velocity. Okay, torque is related to angular velocity. So that I mean to say is, if a body is rotating, it does have angular velocity associated with it. Okay, so torque and angular velocity are in fact related to each other. When there is torque acting on the body, there will be angular velocity acting, there will be angular velocity of the body. Okay, and we often say that the body which undergo rotational motion, which have angular velocity, are under the influence of this torque. But look here, you have no torque acting on the body. You have a torque free motion. There is no external force acting on the rigid body. There is no torque acting on the rigid body, but still you have the angular velocity in the rigid body. Okay, so so this is something amazing. That is, the body is having angular velocity while there is no torque acting on the body. Okay, this is what you call as a torque free motion. The question is, who is setting up this torque? Who is setting up this angular velocity? If the body is under the influence of no torque, so how come there is an angular velocity in it? Who is setting up this angular? That's one question. But the fact is that The body does have angular velocity in torque free motion. Okay, and this is what we call as this is the expression for this angular velocity of the rigid body in torque free motion. Now the question is, if in the exams we talk about the angular velocity components in terms of hg, if we are given this hg, if we are given this theta, if we are given this I, y, I, z, so we can definitely talk about, we can definitely calculate the value of this omega, which we'll be doing later on. Now, in the last, we'll sum up all these expressions, what we have done till now. So for us, omega is equal to omega x I cap, omega y j cap, and omega z k cap. Okay. And if you recall, when we are talking about the steady precision, when we were talking about the steady precision, in steady precision, when we talked about the steady precision of the gyroscope, in this steady precision topic, we stated, we in fact derived this. In steady precision, we have derived already that the angular velocity omega is written as theta dot I cap plus phi dot sine theta j cap plus phi dot cos theta plus psi dot along k cap. As far as this theta dot that time was concerned, this theta dot was the what you called as the angle of nutation. This was nutation. Oh, sorry, this was precision. This was angle of precision. Psi was the nutation, and phi was the spin. This is spin. This is nutation, and this is the precision. So precision, nutation, and the spin. We have already written the angular velocity equation in terms of precision, nutation, and the spin. We have done it in steady precision. Okay. Now, if you recall today's equation in hand, today we have, so the equation that we have today in hand is omega is equal, we recall the equation, omega is equal hg sine theta by I. This is hg sine of theta by I, it's moment of inertia about y-axis, I cap, sorry, j cap, plus hg cos theta iz k cap. This is it. That's it. Hg cos theta iz along k cap. Okay, that's what I added. And there's no the k component. There's no component along x-axis, so I can write that as, I can write that component as 0. There is no component, so we can still write this as, this is omega is equal 0 along I cap plus this. So we can write the angular velocity equation in terms of nutation, spin, and precision. If we compare these two equations now, if we compare these two equations, then we have first this comparison, I components. So theta dot is equal to 0. So that's written here. Theta dot is equal to 0. Okay. The second is phi dot sine theta has to be equal to hg sine theta by Iy. Okay. That is phi dot sine theta has to be equal hg sine theta by I. This is Iy by the way. Okay. And the third and the last component is, phi dot cos theta plus psi dot, phi dot cos theta will be equal to z component, that is hg cos theta by Iz. That's here. Okay. So we are having now the equations in terms of phi dot, psi dot, and theta dot. Then the last one is, if we solve these, sine theta and sine theta will cancel. So the equation that we'll obtain is this. That is, first of all, we had theta dot is constant. Theta dot is equal to 0. That means theta is equal to constant. That's here. Phi dot is equal hg by I, and psi dot is equal to I minus Iz divided by, this is Iy minus Iz divided by Iz hg cos theta. Okay. But hg by Iy is equal to hg by Iy is equal to phi dot. So we'll say hg by Iy is equal to phi dot. We'll get this equation of psi. So if you look at these three equations, the equations for the torque free motion is that our theta is constant, our phi dot is equal to hg by I. Our psi dot is also equal I minus Iz divided by Iz into phi dot cos theta. All these terms are constant. When your theta is constant, when theta is equal to constant, that means this cos theta is also constant. Okay, so this term is our constant. And if you look at hg, hg is the angular momentum about an axis passing through capital Z. We have already stated this is constant. I is also constant. It means phi dot is also constant. Okay, so phi dot is also constant. So we have theta as constant, phi dot as constant, I is constant, Iz is also constant. Therefore, the psi dot is also constant. It means theta is constant, phi dot is constant, and psi dot. These all three terms are constant. It is the same motion as we had done in the solution one. It is the same solution as the solution one. That is a steady precision solution. This is steady precision solution. It is also then the steady precision solution. What does that mean? By saying that it's also steady precision. We have